Hello everyone, my name is Joosen and I'll be presenting How Does It Function? Characterizing Long-Term Trends in Production Serverless Workloads, published at ACM SOC 2023. Serverless computing lets developers use a function abstraction when programming their applications without worrying about where their function runs. Nowadays, function as a service or FaaS abstractions are offered by all major cloud providers. So over the past 5 years, many serverless studies have made assumptions about how these platforms work that may not necessarily hold true in production scenarios. Therefore, to understand serverless systems today, we need more production serverless datasets and insights into their platforms. Our main contributions can be summarized as follows. We characterized 2 traces from Huawei public and private production FaaS platforms over many months, totaling over 1.4 trillion invocations. Our analysis covers 11 metrics from invocations to cold start time. Second, we analyze long-term trends of periodicity and ranking of functions over time. This analysis then informs our approach to function invocation prediction, where we can leverage this data for more efficient auto-scaling while still minimizing cold start times. We evaluate several time series forecasting methods, including some state-of-the-art deep learning models, and we identify key remaining challenges in this domain. And lastly, we have open sourced both traces to the research community. So at Huawei, serverless systems are built on top of containers and Yanrong, which is a scalable distributed computing kernel for serverless workloads. We use machine learning to predict the number of function invocations arriving on the platform for the most popular functions a day in advance. These predictions then inform auto-scaling decisions, and they are used to preemptively allocate pods to reduce cold starts. The table here gives a detailed schema of all the features in each data set, but in summary, we have a 7-month-long data set of 200 functions called Huawei Private, which consists of 141 days collected over a 235-day period. This data set represents traffic from all availability zones in our private internal cloud. We also have a shorter data set of 26 consecutive days and 5,000 functions called Huawei Public, which comes from a single availability zone of Huawei's public cloud. Here are the sum of requests for all functions for the first 7 days in each of our 2 data sets. And there are several clear patterns here, like periodicity and peaks, that I'll discuss in more detail later. So let us first look at the statistical characteristics of the metrics in our data sets. So first, we plot a CDF of the average number of invocations per day per function in both of our 2 traces. Huawei Public, shown in red, has a wide distribution of popularity of functions, and some functions are invoked less than once per day on average, while others are invoked millions of times per day. Huawei Private, on the other hand, shown in blue, has fewer but far more highly requested functions, with some invoked over 1 billion times per day. A known bottleneck in serverless systems is the cold start problem, which occurs when the system does not have enough containers to process an incoming burst, and therefore has to start new containers from scratch, and this adds latency and is something we'd like to avoid. So cold start time is affected, among many factors, by network startup time, container size, and the need to pull containers from registries. So here we show the cold start times present in Huawei Public. Huawei Public runs customer workloads, and we usually know very little about what is actually running. So here we see that about 40% of cold starts take less than 1 second, while over 95% of cold starts take less than 2 seconds. And we have a very long tail at the top end of our distribution. So some major influences on cold start time include package size and runtime languages, which we show here. We believe that some of the long tails of these plots may help explain the long tails of cold start time, as suggested in existing literature. We now move to Huawei Private, where we analyze function delay and platform delay. Function delay is function execution time, shown in blue, and this is almost always less than 1 second. Platform delay is the scheduling and network overhead time, shown in red, and we see that this is almost always less than 10 milliseconds. Platform delay has previously been found to dominate user-perceived cold start times in burst parallel jobs. And burst parallel jobs are created when applications invoke a large number of short distributed functions that require the system to start many interconnected containers. So here we plot the number of instances allocated per function. Some of the larger allocations here could contribute to longer platform delays. We confirm this later in the correlation section in our paper. We see that about 60% of functions only have one instance allocated. However, there are also larger deployments of over 100 instances, and we believe that these large deployments may be part of the reason for the long tail of platform delays. So just to note about these CDF plots where we have multiple curves, all represents the CDF of all values across all functions, while median, min, and max are calculated per function over time. And the CDF is calculated as a cumulative fraction of the number of functions. So we now move on to resource utilization. And in serverless systems, each function has assigned a resource limit for CPU and memory. As is well known, however, functions don't necessarily use all of their assigned resources. So here we show the CDFs of CPU usage and CPU limits for all allocations, as well as median, maximum, and minimum for each function. So we see here that user-specified limits are much higher than usage usually, with 60% of allocations using less than 0.1 cores, but asking for more than 1 core. For memory, we see a similar pattern with around 50% of allocations having a limit of 2 gigabytes while using only on average about 400 megabytes. These allocations are less conservative when we look at the maximum usage curve, but overall there is still a lot of room to decrease this slack by overcommitting resources or using some resource reclamation mechanisms. So we now analyze several in-depth metrics of function invocations. Specifically, we look at periodicity, popularity ranking, correlations, and burstiness of our workloads. And these metrics will then inform design choices of our machine learning optimization approaches later on. So we begin with periodicity, and we can get a fairly complete picture of periodicity in our functions using the power spectral density, or PSD. And we note down the frequency where PSD is highest, and that corresponds to the oscillation with the strongest influence on the function's overall invocation pattern. So we can then plot at exactly which frequencies our functions are most periodic, and on the x-axis we can plot the number of requests per day they have on average. And so both data sets have strong periodicity across functions, mainly at 1 day, 12 hours, and 8 hours. But Huawei Private has a stronger proportion of strongly periodic functions, especially at 12 hours. Huawei Public, on the other hand, has more functions periodic at smaller minute-level intervals or just aperiodic altogether. So if we want to look at the overall periodic behavior of workloads, then we study the autocorrelation function, or ACF, of the total requests for all functions. At a given lag tau, autocorrelation computes the similarity of a signal with a lagged version of itself. So this plot shows the ACF with lags of up to 8 days, and both data sets have peaks at integer multiples of 1 day, again showing the significance of daily periodicity. Again, we can see that Huawei Private has minor peaks at half-day lags, where Huawei Public has troughs, which corresponds to the greater number of points on the 12-hour line on the plot we saw earlier. And this may be due to automated jobs that are scheduled to run every 12 hours compared to less predictable diurnal traffic from external users in Huawei Public. Huawei Public also has consistently larger confidence intervals, suggesting less predictable traffic from external users compared to internal ones. Next, we analyze the rankings of functions over time. This is best visualized using bump charts, showing the functions occupying the top 20 ranks over 2 weeks. So for example, we can see that this top rank here has been occupied by just 2 functions for Huawei Private, but in rank 4, we can see that it's been occupied by 5 functions. We can see that this trend increases for functions further down the ranking. So if we plot the number of unique functions per rank against the rank by median requests per day, then we see that the top ranks are occupied by a very small number of unique functions. And a broadly similar pattern emerges for the first 200 to 300 functions in both Huawei Private and Huawei Public. And so this gives us some idea of how many functions we need to keep track of in the dynamic environment that is our cloud platform, so that we keep track of all of these for our time series models. So we now move on to correlations between top functions in both of our data sets. We see that generally top functions are highly correlated, and this may be because they're called in a chain or because they share a similar diurnal pattern. So another important aspect in cloud data is its granularity and how that affects bursts. So we measure burstiness using sample entropy for the top 10 functions at per minute and per second granularities, and then we see how burstiness is affected by that aggregation. So we see that for several functions, burstiness is much higher at per second granularity than per minute. And so overall, this confirms that per second data carries more information about bursts than per minute aggregations do. So now that we have done this in-depth analysis of function invocation patterns, we build on these insights to improve the efficiency of our serverless platform. So just to recap, function request forecasting can be used to allocate resources, and this can prevent excessive overallocation while still minimizing cold starts. So ideally, such predictions should be fine-grained due to short execution times and fine-grained bursts, as we saw in previous analysis. So we evaluate several time series forecasting models, and we focus on the top 10 functions. And our objective here is to demonstrate the challenges of forecasting such fine-grained data rather than to provide a comprehensive solution. So another important definition we use is fine-grained long-term data, or FGLT. So we define fine-grained to mean that the data sampling rate is much higher than the most significant periodicity. So for example, for per second data, we have 86,400 samples per day. And additionally, we define long-term in this context to mean at least a day. So we've identified two main types of challenges when working with FGLT data. Firstly, if we look at the bottom function here, it has trends over weeks, but also at the minute level. And current models are just not designed to learn this combination of features. Secondly, due to changing rankings and new functions arriving on the platform, each new function would require retraining if we use standard methods, which is too expensive. So the problem of new functions and having too many functions can be alleviated using global univariate models. So we train one model on all functions using the same model weights for all functions, and this is especially suitable as we saw that top functions all exhibit similar periodicities and are correlated. And this is also useful as we can now predict unseen functions new to the platform. So we trained 8 models ranging from FFT to state-of-the-art deep learning models. And as you can see in the table, 2 of the models cannot be trained in this way, but we include them anyway because they are lightweight and widely used. So for training, we selected the top 10 functions by median requests. We have slightly different training setups for Huawei Public and Huawei Private, but for both data sets, we output a whole day at a time. So we evaluate the performance of these models on per minute and per second data. So here we show the results on Huawei Public and Huawei Private at per minute and per second resolutions. We only show the top 5 functions here due to space constraints. So we show RMSE, MAPE, and MAE metrics, and we highlight the best performing model for each function in bold. So we see varied performance across different models and data sets. One notable trend, though, is that the simple models perform quite well, such as FFT and linear, for example, for Huawei Private over deep learning methods. And this may be because of the more periodic nature of Huawei Private compared to Huawei Public. And Huawei Public, which is a bit less periodic and has more bursty workloads, deep learning methods, especially NHITs, do better. So for our fine-grained data, it looks like simple methods tend to perform comparably or sometimes better than neural networks do. So if we visualize the data from the table, then we can see that for per-minute data, most methods tend to approximate the large-scale trends relatively well. But if we zoom in, we can see that fine-grained patterns are predicted much less accurately, and we do still actually have deviations of several hours from ground truth, which is not really acceptable in our use case. For per second data, many models actually have difficulties to train at all because they run into out-of-memory issues, or they simply have a prohibitively long training time. So we could evaluate FFT, but we could only evaluate NHITs if we decreased the input and output window sizes to a much smaller size than the original setup, and then we do get improved results. But even then, we do also have some issues modeling fine-grained structures, and also we do have to invoke our model a lot more frequently than before. So based on the results in these past few slides, we see the following outstanding challenges in FGLT forecasting. So firstly, ingesting long-term data, where long-term means at least 1 week, and secondly, doing so without overfitting. And lastly, forecasting long-term without severe degradation. And we hope to see new models come out in the future to address these challenges. So in conclusion, this paper analyzes 2 large Huawei serverless traces. We analyzed the statistical features of our workloads, as well as periodicity and ranking of functions over many months. And our analysis uncovered several insights which can inform the engineering of future data-driven resource schedulers. And we also highlight the need for further research in estimating resource reservations using time series models. And with that, I would like to thank you all very much for listening and leave you with the link to our datasets and code. Thank you very much.